Hello, so for my combined spectral problem, I have group number 9 with the formula C10H12O. First, started by doing the calculating the degree of unsaturation. The formula for this is 2C plus 2 plus N minus H minus S, so halogen. There's no nitrogen, there's no halogen, so it's just minus hydrogen. So it's 10 times 2 plus 2, and then minus 12 hydrogens divided by 2 equals 5 degrees of unsaturations, which tells me that there's like an aromatic ring of double bonds. Aromatic ring before, so the 5 tells me there's like a double bond attached to the aromatic ring. First, looking here at the IR spectra, you can see like what stands out to me is like this C double bond to an O, the clear signal here around the 1700 range. You can see the C sp3 bonds that I have, because it's less than 3000, and then over 3000 there's an area here which the sp2 carbon 2 hydrogen, indicating like the double bonds in the benzene ring. And then you can see 2 points here around just above the 1500 range, which can often indicate like this the C double bonded to carbon in the aromatic ring as well. Looking at the carbon NMR, you can see there's 1, 2, 3, 4, 5, 6, 7. So there's 7 unique carbons out of the 10. Starting up here, this is around like 190, 192. Relates to a C double bond to an O. And then these are the benzene ring carbons in the shift range of 155 to 125. The C double bond to the carbon double bond to the carbon benzene ring. And then down here, these would be, I should say upfield. So you can see here I wrote, these are like the sp3 and this sp2. These are more upfield and shielded. These are downfield and de-shielded, meaning these are more bonded to electronegative atoms, such as the oxygen, so they're downfield, or they have a higher chemical shift. Where here, they're not bound to a highly electronegative atom, so they're considered shielded. If I scroll down here, make it easier to look at the chart for these first two. So going back, you can see for the IR spectra, just like how I mentioned here. And then for the carbon NMR, you can see the chemical shift at 192, the C double bond to the O. The 155, 125 is the C carbon double bond to carbon benzene ring, and then the 35 to 20 is the single bonded carbon to carbon. Now for the, so this is the hydrogen NMR. You can see here, I wrote there's 5 unique hydrogens. You can see there's 1, 2, 3, 4, 5 signals on the spectrum here. Start with the highest around 10. Often indicates like an aldehyde. That's what I was thinking here. And because there's only one, there's one H, so there's one hydrogen associated with this. The multiplicity is 1, meaning it's a singlet, and there's no next door hydrogens. So this tells me it's probably going to be something like, which makes sense for the aldehyde, because the aldehyde is going to be kind of on its own here, outside of the ring. So this correlates to that. You can see here that this is, so we have 4 hydrogens here, and these are in like that 7 to 8 range. These are pretty clear, like benzene ring location, and there's 4 hydrogens here. The benzene ring is going to have 6 carbons, so that's telling me that there's 2 areas where there's additional groups attached to. these are doublets. So each doublets meaning they each have one next door hydrogen. Then you see 7 right around like free range for one hydrogen here. This means that there's a hydrogen next to 6 neighboring hydrogens. Because it's n, it'd be, and this is n plus 1, so this would be n minus 1 equals 6. As you can see here, this is what I would expect. So this is that 1H, and then the neighboring 6 hydrogens on these carbons. Let's get out of the drawing section. There we go. And then here's the table I did for that one. As you can see, the aldehyde coordinates to that 10 chemical shift. We've got the 7.8 and 7.4. These are the benzene ring, and like I said, there's the doublets. And then the 3 here is that one hydrogen. Like I said, that's the CH bond to CH3. I know this is hard to see in the copying here. And then I have the 1.2. I don't think I mentioned that. Okay, so the 1.2 here has 6 hydrogens, and it's a doublet, meaning it's attached to one hydrogen. So that one would indicate, as I put here, this is like a CH3 attached to CH. So that would make sense, because this is saying that there's next to one carbon or one hydrogen, so it would be CH3 attached to this CH right here. And there's 6 of them, and these are equivalent, so CH3, CH3, so that's 6 hydrogens. And then this is what I anticipate is the 4-isopropyl benzaldehyde. The reason I put them like in this para position is because of how when you have these 2 doublets like this in the benzene ring, these will indicate of the para positioning. That's why they're like this. So like I said, you have the aldehyde attachment here, which is getting you that higher chemical shift as it's attached to that highly electronegative carbon double bonded to an oxygen. You have your 4 hydrogens in the benzene ring, which were indicated right up here. And the CH next to the neighboring carbons is right here. So this isopropyl group. And then these are the 2 identical CH3s that came up as 1 hydrogen, unique hydrogens to equal 6 specifics that are bound to each to the CH. So my proposed structure is this 4-isopropyl benzaldehyde. And that's it. Thank you.